Hello, this is a bonus little second video I figured I'd make to follow up because when I went through and was showing how we come up with those correct moments of inertia, I basically just skipped over this value here, this 2.175 times 10 to the 10, and I basically just took it from mass and was assuming that it was correct, but then I realized that I probably should not have done that. So what I'm going to do, I do have the mass window here. It's kind of sized funny. I'll make it a little bit taller. It's just pondering. So we have our values here looking at the web. So I know how much steel is in each cell, where exactly. I can scroll up and then hold right click to pan around. So you can see where the bars are. The 10M bars are pretty small in the cross section. I have to really scroll in here to be able to see these little orange dots that show up. So what I'm going to do is use these values and go ahead and figure out what that cracked moment of inertia is, given that we already know what our KD value is. So that's the location where those first moments of area balance out. So I've got this. I'm going to quickly just sort of draw a boundary element here to illustrate. That's a bit bigger, not to scale, just so that we have something there. And then within this web, so we have, I'm going to try and do this more or less correct. So we have 6 layers of steel. Oh, and then we also, I can't forget, we also have the boundary element down here that kind of goes this way. Boy, that looks great. Okay, so we have bars in each end, basically in the outer cells, and then spaced every 400 the rest of the way, we have these layers of steel here. Now, since these are 10M bars, they each have an area, a bar of 100 square millimeters. So we'll put that in there, and you'll recall that using the stiffness that we looked at before, we have an N, so our modular ratio is equal to 20. So we have that. We also found from before that our KD that we had was equal to 741 millimeters, and this boundary element is 790 long. So actually we do have our boundary element that is over here. Perfect, so we have that, and so I'm just gonna write KD equals 741. And then the question is now, since we are fully on the tension side, that says the word tension, if you could read that. Since we're on the tension side of KD, what is the crack moment of inertia? And I have not rehearsed this. I'm really hoping that it just happens to work out to the same number. So for each of these bars, we can number them. So I'm just going to start with this one here. I'll switch over to red. So I'm going to label these, so in mass, they are, all the cells are labeled, so there are 11 cells all the way across. So what I'm going to do, though, is simply just label these bars as being, I'm just going to label them 1 through 6. So bar 1, 3, 4, 5, and bar number 6. This is riveting stuff, and actually just from the software, like I said, that I had before, what I'm going to do is these D values that show up here. So you see for the bar closest to the compression zone, that distance is 900 millimeters. And then basically since they're spaced at 400, those numbers increase by 400. So we have these values here. So I'm just going to quickly write down these D values. In fact, you know what? I'll put it like this. So right here, this bar all the way measured from this edge here, so the extreme compression edge. This D value is equal to 900 millimeters. So I'm just going to write 900 there. The next one that we have is 1300 because they are spaced apart at 400 center to center. So that's 1300. Whoops. I wrote 1310. Wow, what a twist. All right, now we have 1700. It's actually hard to do this in your head when you have the pressure of the camera rolling. I wouldn't make a good stuntman, I don't think. And then finally, 2900. So that's, once again, the distance for each of these. And so, as I said before, we don't take into account the actual shape of these bars, the fact that they're circular within the wall. We're really concerned about that AD term. So looking at the parallel axis theorem, how do we take a moment of inertia measured about the bar and translate it to being measured about this KD location? And the way we do that is with AD squared. So what I'm going to do for each of these, so starting with bar 1, so ICR web, I'm just going to do S1. Our first term is going to be 0, but then plus AD squared. So since we're on the tension side, we don't need to do n minus 1, we can just do n. So I'm just going to do n times AS1, and then we have D1 minus KD squared. So actually, first of all, if I write a proper 2, if we go ahead and substitute our values in, so we have 20, and that is times 100. And that's just because the rebar is 20 times stiffer than the grouted masonry. And we are going to multiply that by this 900 millimeters that we have here. 900 minus the 741 millimeters, and that distance is squared. And so that is going to give us an answer. I actually have to type this in my calculator because I haven't done this yet. 20 times 100 times 900 minus 741, square that whole bracketed term. Okay, so I'm going to do this in scientific notation here. So I've got 5.056, and that is times 10 to the 7, measured in millimeters to the 4. Okay, so there's that one, and now what I'm going to do is I'm going to do the same thing for the second bar, the third bar, the fourth bar. And so I'm going to put my values here, and so once again, the area is going to be the same, 20 times 100. It's going to be the same for all of these, but now we have these different distances. So now we have 1300 minus 741 squared. We have the same thing, but it's going to be 1700, 2100. I'll scroll down just a little bit. Where's my mouse? There we go. 2500 and 2900. So we're going to do this each time. I'm just going to skip ahead to save the time of me writing this out. All right, now with the magic of video editing, since I'm such a wizard at that, what I've gone ahead is filled in the rest of it just so it's all there. But basically, it's the same formula, just we have these different distances. And so we expect that as we get further away from KD, these I cracked components are going to be getting larger and larger. So if I go ahead and I substitute, instead of using 900 for the distance, I use 1300. What I do if I put that in my calculator is I get 6.250. So I'll write that out. And that is times 10 to the 8. So we're already quite a bit bigger. But that makes sense because our distance is quite a bit further. Now if I go back and I change that 1300 now, looking to a 1700, so I'm going to go and change that on my calculator, just so I still type it out again. 1.840, 1.840, that's times 10 to the 9, so these numbers are getting quite a bit larger. However, it's the distance squared, not just the distance that's in this formula, so it's not just going to be a linear relationship, it's a quadratic actually. So then going from 1700 to 21, I'm just going to go back here and make the same change. So times 21. All right, 3.694. And that is also times 10 to the 9. Do the same thing now. From 2100, use 2500. All right, we get 6.188. Times that same power, times 10 to the 9. And then last but not least, we're going to change this, put in 2900. This will be our largest value, the bar that's furthest away, 9.323. Okay. And that's also times 10 to the 9. So now basically, since our I cracked of the web is equal to the sum of for each of these in the web from I equals 1 to the number of bars that we have, then we can go ahead and we can add these up, and I'm going to do that right now. So saving you all the time of me punching these in, once again, video editing, we can add these up, basically this plus this plus this, all 6 terms, and putting in my calculator based on what I put in here, I get 2.172, and that is times 10 to the 10. That's pretty close. I mean, especially when it comes to the rounding of these larger terms. I would like to think that's where that slight difference is, because when you put it for mass, we get 2.175, and mass just uses the exact values. So I'm going to say that's good enough for me. But if you want to call me and give me a hard time, then that's fine too. In any case, this is sort of a bonus post, just sort of going through how we get that value in the web that I had assumed. Hopefully it makes sense. But thank you very much for watching, and hope you have a great rest of your day.